quality and what are the issues, what is basically the power quality. We discussed all these things, and we said power quality is voltage quality. Then we discussed what is point of common coupling, and we gave these examples, and then we were talking about the survey results on the causes of power quality problems. The perception of clients is different than the perception of utility companies. Then the justification of interest in power quality, why the harmonics levels are increasing in power network, load equipment is more sensitive, this all things we discussed. Then the protection against power quality is basically the protection against interruption of production, which is very costly. Even if for few minutes in one day there is no electricity, so it is not just a matter of a few minutes. It costs only in the North America more than $100 billion every year. So this is what actually we can achieve if we have a better power quality residential customer. Then we discuss the different issues. What are the power quality impulsive transients, right? We saw this thing, and then impulsive overvoltage and oscillatory transient. All these things we have discussed. Then voltage sag dip for a few cycles. We have discussed this thing, and what problems voltage sag may cause, and the example of voltage sag if you have single line to ground fault, or if a large motor is starting, then it draws a lot of current, 5-6 times of the nominal current or rated current of the machine. So it will cause a huge drop in the impedance of the line and causing. Then swells, temporary over voltages for few seconds, we have few cycles, right? So we discussed this thing, causes and what problems it may cause, and then example of temporary over voltage. Then short interruptions. This is what we were saying, that for few minutes of cycles, if there is no electricity, so it costs a lot of money, right? And it causes the following problems, impact on industrial products and those things. Then we were talking about under voltage for more than 1 minute, so we may call it brownout also. And then over voltages. So everything we have discussed. Sustained interruptions for more than 1 minute, then we call it sustained interruptions, right? And then we were talking about voltage unbalance and how we are tackling this situation. And in transmission lines, we use transposition of conductors by shifting the position of the conductors. And then we were talking about waveform distortions. There are 5 types of waveform distortions: DC offset, harmonics, interharmonics, notching, and noise. So this is DC offset. It may cause the saturation of transformer core, right? And then we were talking about the harmonics, how we can use the Fourier series. And today we will discuss briefly the Fourier series also. I know you have already studied in your undergraduation, but just to have a basic idea how to use the Fourier series and how to simplify the calculation, that we will study also today. Then different types of single phase diode bridge rectifiers, you see, square wave, and what are the harmonics created. And if you have RC load, diode bridge rectifier with RC load, it causes lot of harmonics and lot of THD in the system. So we were talking, and then we were talking about what problems harmonics cause, okay, increase in losses in conductors, and the reason we saw like skin effect, ohmic losses, and then we were talking about the ferromagnetic losses like hysteresis losses, eddy current losses. So these are very important issues. If we have the harmonics, high frequency is there, so hysteresis losses are proportional to the frequency, while eddy current losses are proportional to the square of the frequency. So we will see perhaps again this little bit, and then degradation and considerable reduction of capacitor's life. Capacitor may attract higher harmonics because the reactive in capacitance it value decreases and it may attract higher harmonics. Then voltage distortion, heating and torque pulsation in motors. Yeah, we discussed heating and pulsation of torque pulsation in motors, and we discussed how the fundamental frequency is generating rotating magnetic field in the air gap between stator and rotor, and a stable torque is produced and the rotor rotates in the same direction as rotating magnetic field. And then we have, suppose, voltage distortion at the terminal, then the fifth harmonic may be there, sixth, seventh harmonic currents may flow in the motor, then the fifth harmonic, as we will see today also, and why fifth harmonic is a negative sequence harmonic and seventh harmonic is a positive sequence harmonic, we will see that today. And so fifth harmonic will generate the torque in the opposite direction, and it will be having the frequency 5 times of the fundamental. Although amplitude is 1/5, then, but still it has some parasitic effect. And the seventh harmonic then is the positive sequence harmonic, so it will generate the torque in the same direction as fundamental frequency is generating, but the frequency is 7 times, so it will rotate with the 7 times faster than the fundamental frequency which generate the rotating magnetic field. So this is very important to know why there is a heating, and then heating is there because you are having harmonics, and fifth harmonic, 7th, 11th, 13th, 17th, 19th, those harmonics are there, and then they will generate extra losses in the core, in the rotor and stator material because of the ferromagnetic losses, hysteresis losses, and the eddy current losses. And then large neutral current, of course, we know that in normal balanced system, if we have IA, IB, IC, the sum we can say, okay, because of the Kirchhoff's current law, the sum will be 0. But because they are 120 degree apart, right, phase shifting. But if you have the zero sequence current, then they are in the same phase. So instead of cancelling each other, they will add up. So that's why the neutral current problem may be there. Then we're talking about the standard 519. Initially it was 1992, but it has been updated in 2014 and 2022, and they have little bit changed. So there are some minor changes, but for us they are not any major change. Then we were talking about interharmonics, same type of problem, and then we were talking about the notching, drop of voltage during commutation of current, because there is a source inductance which will prevent the current to reduce to 0 instantaneously, so it will take some time because of inductance, and another set of thyristor, it will take some time to build up the current, so there is a commutation overlap, and because of that we have the voltage drop. So all these things we have discussed. So you see voltage notching, and then we observe at point A here, and then we calculate the depth and the width of the notch, and then we can calculate the surface. And there are certain norms, how much